hash function will use lots of non-invertible functions in its own operation. So, for example, if I ask you, I've got two numbers that add up to 100.
Yeah.
What are they?
Yeah.
I don't know, right? They could be
50-50 or whatever, yeah.
And also we have this counterintuitive thing where we can brute force these passwords in some way. And you think, well, how could that be done if you can't reverse it? So let's think about if you broke into a website, how would you break the passwords in that website? You've just got a list of hashes. Right? What do you do? Well, each hash looks random, and there's no way I'm saying to go backwards and undo all of that jumbling and iteration and that summarization and get back to the original password.
So, I mean, I think the concern is if the attacker gets that file and can see what the salt is, can't they just reverse it? Or are you saying they can, it's much more work?
They can hash password guesses with the salt, right? So let's suppose my salt is 1234, right? They could try 1234 password 1, 1234 QWERTY, 1234 bad password, 1234 correct horse battery staple, right? And they can try with different ones. The salt doesn't add secrecy, it adds randomness.
Data brokers are collecting and selling your data to governments as well as companies. Now, not just your own government, but also to hostile states and to almost anyone with a credit card. This includes data like real names, addresses, phone numbers, relatives, and even photos. That's what makes it such a common vector for doxing, stalking, harassment, identity theft, and fraud. Now, I've often seen on YouTube comments that people saying, we shouldn't have to pay for someone to go and remove our data. It shouldn't be collected in the first place. Agreed. That's a perfect world, which doesn't exist, unfortunately. Our data is being sold by companies. You need to get your data removed from the internet. The way I look at this is that you have three options. If you have very little money, but you have lots of time, you can go and manually remove your data from the internet yourself. But you've got to find the websites that you're going to remove the data from, and you've got to continuously do this because your data will come back. Now, that's not an option for me. I just don't have the time to constantly monitor data broker websites and play whack-a-mole with these data brokers to get my data removed. I would rather pay for a company like DeleteMe to do that for me. And that's the option that I use. Now, there's a third option. If you're a multi-millionaire and you have lots of money, you can pay someone to go and do this on your behalf. I know people who offer this service, but it's not cheap. So there's your three options. I personally prefer using DeleteMe. So if you're interested, you can join using my link and get 20% off a DeleteMe consumer plan. So go to joindeleteme.com/Bombal and use promo code Bombal at checkout or use the QR code on screen. That once again is joindeleteme.com/Bombal, code Bombal. Hey everyone, David Bombal back with the amazing Dr. Mike Pound. Mike, great to have you back on the show in 2026.
Thank you very much.
So Dr. Mike Pound is an expert in cryptography and all kinds of things, even though he doesn't admit it. Mike.
I don't admit it.
You're an expert. So I've got to ask you this because I have made videos in the past where I say hashing is a one-way function. And then people give me lots of like crazy comments on YouTube saying, David, you're wrong. What about rainbow tables? What about this, that, and the other? So I'm going to hit you with the first question, then perhaps you can take us down, sort of the journey on this. Is hashing encryption?
No, right. Hashing and encryption sit under the umbrella of cryptography. They are things that we do, but they're not the same thing at all. And they have very different use cases. And actually, I think one of the interesting things about cryptography isn't just technically how things work, but also how you then use those things in very specific ways based on how they're different.
Mike, could you just give us a little bit more detail about the difference between hashing and encryption, just for people perhaps who didn't get that short summary?
Encryption is the idea of jumbling up a message in such a way that you can't read it, right? Or no one can read it. And then with your secret key, you're able to reverse that jumbling process and return the message back to its original state, right? So it's a kind of two-way function. You can encrypt and then you can go back and decrypt, but only if you have the key. Hash functions are what we call a one-way function, right? So they basically irreparably damage the structure of a message such that you cannot go back. But they're still super useful because they succinctly summarize the contents of that message, even if you don't know what the contents were. Right? So you take your 5 gigabyte file, you use SHA-256, and you get a neat 256-bit short, succinct summary of that file, which will always be the same. If you put that 5 gigabyte file in, you'll always get the same hash function out, but it is generally speaking unique to that file. Right? You're not gonna be able to find with any likelihood another message, but also hashes to that same thing. And so you can use them to check that a file's been changed. You can use them to check that nothing's accidentally been changed on a disk. You can use them to check that a message that you sent me has not been tampered with on some router between you and me. Right? And that's an incredibly useful thing. Hash functions are literally used in almost every protocol on the internet and in TLS and for file storage, for digital signatures. They're used everywhere because they allow you to very briefly summarize a message and then check that it hasn't been changed later.
And they also use in passwords, correct? So we don't store the password.
Yeah.
We don't store the password, we store the hash or the password or something. Is that right?
Yeah. You don't. Suppose you're a company and you're trying to authenticate users and have them log into your system, what's going to happen normally for password-based authentication is they type in their password on your web interface and the password goes to your server and you look at it and go, yeah, they're allowed in. That is who they say they are. The problem with that is that kind of implies that you have a list of everyone's passwords in your database. And then you've got to ask what happens if someone at your company isn't trustworthy or there's a breach in your company and all those passwords get stuck out on the internet. Right? Yeah. That's a huge problem. It's even worse because people tend to reuse their passwords so often, right? Even though we tell them not to.
Yeah.
They do it. So what a hash function does is essentially mask that password. It hides it, right? It irreparably changes that password into a form that doesn't look like the original password in a way where I couldn't look at it and go, yeah, that's the old password I know, and then I can use it to log in. It does that by essentially jumbling up the bits and bytes of the password and overriding things and deleting information and things like this in such a way that password is gone. Right? And all that's left is this hash representation of it. And then logging in is quite simple. All you do is you take my incoming password, you hash the incoming password, and you look at the hash that you've got in the database, and you see if the hashes match. And that is quite a neat trick because it allows you to verify that I knew my original password without you actually ever knowing what my password was. Right? You can do the hashing on the client side if you want, if you're really down on security, to make sure that no one at any point has ever learned what that password was. You just know what the hash was.
And the same password results in the same hash. Is that correct?
One of the interesting things about hash functions is we call them a pseudo-random function. So that's a function that you put in something that isn't random. Let's say all zeros or all ones or the works of Shakespeare, right? Which they're not random because they're all fixed and written down that we all know what they are. And you get something that looks completely random out, right? It has the appearance of being random. But actually, these algorithms are defined very carefully in their spec. There's no randomness in them. And so actually, if you put the entire works of Shakespeare into a hash function, you will get the exact same hash every single time, right? And that's incredibly useful for things like password authentication, but it's also useful for things like digital signatures. If you wanted to prove that I signed a document, I could sign the hash, and you could also verify on that hash. And as long as those two hashes came out the same both times, it's going to work, right? If the hash was random, it wouldn't work, right? You might as well just produce a random number. It's not useful for summarizing a file because the file hasn't changed, but the hash has. So it has to be what we call deterministic. Right? The hash function takes the same file and outputs the same random looking hash every single time.
And if I took the works of Shakespeare and I added another full stop or period or whatever you want to call it, or exclamation mark somewhere in that document, would the hash change?
Yes, and it will change not even a small amount. It will change almost entirely. So I've actually done this exact thing for part of my teaching. I loaded up the entire works of Shakespeare and I hashed it. And then I went into the middle of one of the books. I couldn't tell you off the top of my head which book it was. And I changed the word die to pi, right? Which totally changes the meaning of the paragraph, to be fair. And the hash, about half the bits flipped in the hash output, right? So we're talking about tens of thousands of characters in ASCII. We only changed one, half the output's changed, right? That's how powerful these hash functions are. Any hash function that didn't do that, that didn't have this kind of avalanche effect from input to output, wouldn't be considered a good hash function. It has to look completely random. It has to, for everyone observing, it has to look like I've just flipped coins, even though I haven't actually. I've run this algorithm that does the same thing every time.
So, Mike, just before we get into the nitty gritty or into the weeds, is a hash function reversible?
No. A hash function. So maybe we could dive a little bit into the difference between encryption and hash functions to explain why it's not reversible.
That'd be great.
An encryption function has to be reversible because otherwise it's totally useless, right? So if I take a book and I want to encrypt it, what I don't do is rip the second half of the book out and throw it away, right? Because if I do that, there's very little chance I'm going to be able to reconstruct the second half of that book.
Yeah.
So what you actually do is you take your book and you jumble up all the letters and numbers in such a way that it's the same length as the book was originally, but reads like complete gibberish, right? That's the idea. But importantly, it's the same input and output size, because that way you have a one-to-one mapping from potential input books and jumbled up rubbish books, right? A hash function is very different. A hash function is more like you take your 500-page book and you write a one-paragraph summary of it,
okay.
Right? Now, given a one-paragraph summary of a book, you aren't going to be able to reproduce word for word, punctuation for punctuation, that book, right? You've just thrown away most of the information. It's not there. So yes, the summary summarizes or otherwise explains what's in the book in some way, but you can't possibly reverse it to go back because you deleted everything. And a hash function works a lot like this. So unlike encryption, a hash function will use lots of non-invertible functions in its own operation. So for example, if I ask you, I've got two numbers that add up to 100.
Yeah.
What are they?
Yeah.
I don't know, right? They could be
50-50 or whatever, yeah.
Okay. Without one of them, you're not going to be able to tell me what the other one is.
Yeah.
There's a lot of operations like that in a hash function where you're taking bits of message, you're adding it or doing other operations to it with other bits of message, other bits of book, such that they all override each other and interact. And by the time you get to the end, you've just thrown away most of the book. Right? It's been used to create the hash function, right, or to create the summary, but it's gone and you can't get it back. And so they're very useful where you need a succinct summary, digital summary of a file, but it's completely useless if you ever want that file back again. That's what leads to such interesting use cases for hash functions and why it's so different to encryption.
Yeah.
Encryption has to be one in, one out, right? There's a set of different encrypted messages and they're just one to one because otherwise it doesn't make any sense, right? You couldn't possibly reverse it. But for hash functions, it's not one to one, it's many to one. And that means you don't know. There could be many books that go to the same rough summary, and you wouldn't be able to tell which one it was. You would be able to go forward and summarize books still. I don't know if this book analogies make any sense.
No, it does. I think the analogy I've always heard, right, it goes by different variations. I'll give the South African one that we use for years. If you take a steak and you make mince out of the steak, you can't make a steak out of mince, even though I'll use my bad sarcasm. They try and do that in some parts of the UK. In Tesco, they'll sell you like a steak that's made from mince, but you're losing value or something. Or some people say you take food and you chop it up into little pieces. You can't get the original food back. Is that a decent analogy, or is that kind of not really a good one?
Yeah, I think that's close enough, right? I mean, the book analogy falls down a little bit anyway because your summary needs to be almost random looking, right? Because the whole point is you're not meant to be able to tell anything about the original input. Mincing up a steak, you couldn't tell me what shape that steak was or whether it was probably couldn't tell me whether it was a ribeye or not, right? Because all that information is gone. It's just minced nonsense. And that is kind of the whole point. The only thing that's really important is that if you put that exact same steak in 2 times, you would get the exact same mince, right? And that's very important because we use the uniqueness of these outputs to do things like digital signatures or to verify passwords and things like this.
Yeah, I think one that a lot of people have encountered is if you download a file. So I'll just use the example. I go to Kali Linux and I download an ISO. That thing is like 5 gig or 4 gig in size. And then they give you a hash of that file and say, if you want to make sure that you got the original file, then check this hash. And then you could run a SHA or MD5 or whatever against that. And if I understand this right, correct me, Mike, 4 gig file is massive. 128 bits is tiny, or 256 bits is tiny. You can't use 256 bits to get back 4 gigs of data.
No, it's all gone, right? It's basically all been stamped onto the same location and jumbled up. And so you can't tell what came from where. It doesn't mean it isn't useful, right? It allows you to, with a high degree of certainty, know that your download is correct and it hasn't been interfered with, because the chances that someone could do something nefarious to your download and get the same hash output, it's unbelievably unlikely. So it's all about probabilities, right? It's not to say there aren't multiple versions of Kali Linux that could hypothetically exist that hash to the same thing. It's just that no one will be able to find them, right? And so if your hash doesn't match, it's much more likely that something's gone wrong with the download or someone's interfered with it than it is that you've got two Kali Linuxes, one of which is nice, one of which is nefarious, with malware buried in it, and they both hash to the same thing. Right? So you can be pretty sure if the hash doesn't match, but you won't be able to get the file back. Right? It's a check. It's not a reversible process.
Can you explain what hashing actually is? Because I think a lot of people understand the concept of, okay, I need to encrypt my data so that hackers can't see it. But like, how is hashing different and how does hashing actually work?
So, as you say, encryption is usually about keeping things secret, right? So you're taking something, you're scrambling it up in such a way that you can reverse that process and get the original file back, but someone else can't because they don't have access to some secret key or some other information that they need. Hash functions aren't the same as that. The goal is not to be able to reverse the hash function. The goal is to summarize some document or some file in a succinct way where usually it's unique to that file, but not always, and it gives away nothing about what that file is, right? So essentially, you could think of it, if you just replaced it with a random number generator, you put in a file and you get a random number out that bears no resemblance to that file at all. So you can't go back because it's completely random, except that in a hash function, you always get the same output when you put the input in. So the same document leads to the same hash function.
Yeah, so I've seen this thing, right? If I hash I'll just use MD5. MD5 is 128 bits, right? I get 128-bit value. But if I hash B, the letter B, it's still 128 bits, right? But it's totally different number. And the same with C. Is that correct?
Yeah. I mean, actually, the technical term that we use in the cryptographic community is a pseudo-random function, right? And so that means that it has the appearance of being random. And part of what makes a hash function good is how random it appears. So even with something like MD5, which has some security vulnerabilities, you would expect that a tiny change in the input of a single bit would, on average, flip half the bits of the output. So you've got 128 noughts and ones. They're completely random looking. You change the input, you get 128 different noughts and ones. Some of them change, some of them don't. It looks like someone's just flipping a coin.
Give us some examples of hash functions and then explain why MD5 is bad.
Yeah, okay. So MD5 was prevalent, let's say, in the 90s and the early 2000s. It was replaced pretty much by SHA-1, which is a 160-bit output. So that's 160 zeros and ones. Since then, we found collisions with SHA-1 and we've moved on to things like SHA-2, of which you have things like SHA-256, SHA-512, and then there is also a SHA-3, which is very, very different. The problem with MD5 is the fact that it's too easy to find a collision. So let's imagine that you've got your MD5 is outputting 128 bits, right? So, and you can hash any file you like. You can create any file, like a PDF or a video or, the content of a website. You can put these all into MD5 and still get 128 bits of output. That means there are more possible messages than there are potential MD5 hashes, right? Because there's literally 2 to the power of 128 different versions, all the combinations of noughts and ones that are 128 long. But there's a lot more files than that, right? Because not all the files are exactly 128 bits long. And that means, by definition, some files will hash to the same thing, right? Now, the chances of you finding such a collision are pretty slim for a hash function. But unfortunately with MD5, it has some mathematical weaknesses that make actually it's not so difficult to find a collision. So I might be able to find 2 files that hash to the same thing. And that's a huge problem because often you use hash functions to prove that something is unique and hasn't been changed. So for example, suppose you digitally sign a message over the internet that's, let's say, transferring me £10, but I managed to change that message to be transferring me £100, but the signature still matches, right? Because the hash function is the same. That's going to cost you £90, right? You don't want that.
So collisions are, because I'm slow, where you have 2 different input pieces or values or whatever, and they result in the same hash. Did I understand that correct?
That's correct. Yeah. And, in MD5, it's quite easy to find a collision. In SHA-1, it's hard, but it's still possible. And in SHA-2, no one's done it, right? No one's achieved that on SHA-2, right? Now, I have a track record of saying a hash function is fine, and then someone breaks it the next day. So I'm not going to say it can't be done. SHA-2 is actually mathematically and structurally quite similar to SHA-1 in the way that the algorithm has been designed. So in some sense, you could argue that because SHA-1 has weaknesses, those weaknesses may exist in SHA-2, but no one's really found them yet, or at least the work that would be required to get SHA-2 to collide would be too difficult to bother with, right? Too many GPUs, of too much compute. No one's going to bother with it.
So today, in today's world, which one would you recommend we use, if any?
Almost everyone uses SHA-2.
So is it like 256 or 512, or doesn't it matter?
No, it doesn't really matter. In fact, 384, which sits somewhere between the two, gets a look in as well. One of the things to bear in mind is that finding a collision in SHA-2, if you're just hashing random things, is quicker than you think because of something called the birthday paradox. So
yeah, you could explain that.
We've got a video on this on our Computerphile channel, but
I'll link that below. Yep, that's a great video.
But the general idea is that as you start to get hashes, you're more likely to find a collision because you already have a long list of hashes that you've got. And so for a hash function like SHA-256 that has a 256-bit output, in actual fact, you'll find a collision after about 2 to the 128 operations, which is half the size, right? And it's a square root in terms of how fast it is, much, much faster. So one of the problems with MD5 is because it only has 128-bit output, the search space to find a collision is actually only 2 to the 64, which, on a modern powerful machine is not insurmountable. And so that's another one of the problems with it, right? We want longer outputs. So by definition, SHA-256 is less good than SHA-512, but at the moment we can't brute force 2 to 256 or 2 to 128. So in some sense, maybe it doesn't matter, but it's just worth bearing in mind. And for the sake of a small amount more storage, you could argue it's worth doing with bigger hash function.
So explain the birthday paradox or birthday attack again, just so that people give us a brief overview.
Yeah. The birthday paradox is unrelated to hash functions. It has implications for hash functions. The idea is that if you have a room full of people, the chances of 2 of them having the same birthday is actually really quite high, right? To the point where if you have 23 people in a room, the chance is 50%, which seems really weird, right? You've got 23 people, there's 365 possible birthdays, not including late years. And so you would get, 23 over 365 or something like this. But actually, that's not how the mathematics works at all, because we're not testing whether they have the same birthday as me, which would be 23 over 365. We're testing whether any of them share a birthday. And there's loads of different connections between different people. So there's loads of opportunities for them to share a birthday. So actually, once you get to about 40 or 50 people, the chances that they share a birthday, it's close to 1, like close to 100% certainty, even though there are loads of birthdays not accounted for in that group of people, which is kind of counterintuitive. And the exact same thing happens with hash functions. With hash functions, you've got multiple messages being hashed to the same thing. At some point, you're going to find a collision, and it comes sooner than you think. Right, because of the fact that you've got all these hash functions that could collide with one another. And so all it means in practice is you need to use a long enough hash function that even given the birthday paradox, you still won't find one. That's the idea. And, most modern hash functions, SHA-2, all of them are basically impervious to this, right? They've got too big an output for it to be much of a concern.
So, Mark, I got to hit you with this because I have seen this on a lot of YouTube comments. And for people who are watching, I read the comments. So the comments that come on these kind of videos are, David, you're wrong. Hash functions are reversible because you forgot about rainbow tables. Or they'll say hash functions are reversible because some passwords are not 256 bits or whatever. So let's start with rainbow tables, because I think the confusion is people think hash functions are reversible because that's exactly what a rainbow table does, according to some people.
Yeah. So let's think about how you store passwords, right? You store passwords by hashing them and then storing that hash in a database. And the argument is that the administrator of that website or someone who breaks into that website can't read your passwords because they're stored in a kind of unintuitive, random-looking hash way. The problem is that there are many different kinds of passwords, right? They're all, there's lots and lots of potential passwords. There's not that many potential hashes comparatively. And also we have this counterintuitive thing where we can brute force these passwords in some way. And you think, well, how could that be done if you can't reverse it? So let's think about if you broke into a website, how would you break the passwords in that website? You've just got a list of hashes. Right? What do you do? Well, each hash looks random, and there's no way I'm saying to go backwards and undo all of that jumbling and iteration and that summarization and get back to the original password, right? Because a lot of the time you're going to get left with a number and you don't know which two numbers added together to get to that number. So what do you do? Well, what you do is you try and guess what my password would be. So you say, I think Mike's not got a good password management policy, right? And his password is password 1. So you hash password 1 using the same algorithm you know they're using in the database. And you get this kind of example hash, which you then look at and see if any of the users have that hash. And if they do, you know they were using password 1 or another password that hashes to the same thing, right? It's neither here nor there. That's when you know you've broken it. So in some sense, you're breaking the password by going forward from the password, from a guessed password to a hash, rather than going from backwards from a hash to a password. Right? And that puts a lot of power with the people whose passwords it is. Because if my password is hard to guess, you aren't going to be able to do that. Right? So suppose my password is not password 1, and it's, let's say, 20 random numbers and letters. But good luck, right? Trying to guess what that is, hashing it and noticing that it matches in the database. Right? You're not going to be able to pull that off. So hash functions have the appearance of being reversible because you can, pre-compute hashes in a rainbow table, or you can guess passwords at a login prompt. But actually what you're doing is just trying out new hash functions. You're not actually undoing a hash function that's in the database.
So what is a rainbow table? Is it just a bunch of hashes that people have created based on some passwords? Is that what it is? Yeah?
This was, there are more modern versions of rainbow tables that try and make this process a bit faster. But this goes back to maybe when, old Unix systems where we were limited to 8-character passwords, or even Windows XP, but didn't have a particularly strong hash function. If your hash function output is short, or the number of characters you allow people to have in their password is short, a lot of passwords, there's not going to be that many hashes, right? Yeah. If you only allow 8 lowercase letters, you've just got 26 to the power of 8 different possible combinations. Not that many, right? And so actually, you could just fill a hard drive with all the possible combinations of letters of 8 characters and their hashes. Pre-compute them on a server for a while, and then when you break into a system, just have a quick look at any of the hashes, look them up in that database, and you immediately have their password. So what a rainbow table does is pre-compute loads of example password hashes to try and make the lookup faster, right? What it doesn't do is reverse any of those hashes. So, because you can't do that. So it only works when you are able to pre-compute a bunch of stuff. So if you add salt to the password, so randomness to the password, that makes it almost impossible. If your passwords are very long, your rainbow table will be much too big and you couldn't compute it, right? So, it always comes down to having a good password, right? That's the idea. But it's so that people can't do this easy hash, forward hash function approach.
So in other words, a rainbow table is pre-computed hash functions, and all you're doing is you're matching the hash that you've captured as an example on a sniff or whatever to that hash. Right. And then because that table, because they made the table and they know which password gave you that hash, you know what the password is. So you're not reversing it. They did the forward method and you're just doing a lookup on that table. Is that kind of right?
So maybe you hash password 1, right? And you get a hash that starts with FF2A. You put FF2A in your database next to password 1. And then if anyone with an FF2A hash function turns up in one of your leaks, you just quickly look it up and go, oh, that was password 1. We now know how to log in as that person. You don't need to reverse the hash. You've just guessed a bunch of passwords or a bunch of common words and pre-computed all the hashes for them. Pre-computing hash functions allows you to do the attack at, should we say at runtime, much, much quicker, because you get access to these passwords that have been leaked, these hashed passwords. You can very quickly look them up. It's slower if you have to compute all those hashes over and over again. So another reason, along similar lines, people use password lists, right, to try and break passwords more quickly because of the idea that people might use the same passwords multiple times. So, start with the obvious one before you start doing the really difficult stuff.
Yeah.
This is very different to encryption. Encryption, there is always a way to reverse it. Otherwise, it's not encryption.
Yeah, exactly.
It's just that without the key, you're missing part of the algorithm that allows you to do that. So essentially, it looks like random nonsense, but there are some known steps that would allow you to reconfigure that back into the original. You just can't do it without the key. That's a very different concept.
So you mentioned salting. Can you explain that?
Yeah. So The problem with rainbow tables is that someone can pre-compute a bunch of example passwords or brute force through all the character combinations, put them all on a big file, and then look them up easily later to attack people's passwords. To avoid that, what you do is you make sure that people who have the same password or easy passwords don't hash to the same thing. Right? And you do that by appending some random data to their password before you hash it. So as an example, let's imagine my password is terrible again, right? So my password is password1.
Yeah.
That's going to always hash to the same thing.
Yeah.
So if anyone sees that hash in the database, they're going to know, oh, it's got password1. So it's obvious, right? It's the same hash as everyone else.
Yeah.
However, if you put some random numbers in front of password1, so maybe my password is password1, but my hash function is calculated on 12789 password1, it's going to have a different hash.
Yeah.
And that way it won't be so obvious that my password is password1, right? You'll still be able to guess it. Now, the important thing that people sometimes don't realize about these salts, these random initializers, is they aren't a secret, right? The password is a secret, but they are just stored in your database next to your username. And or if you look in Linux, you can see them in the shadow file, right? Between different dollar symbols. And that's because you need to be able to test with that salt at login, right? But you don't want to be able to reverse engineer it. A nice way of looking at it is, imagine you had 2 different salts that you were using in your database. So you have a list, let's say you have 10,000 users, and each of them has 1 of 2 different salts. You've now doubled the number of potential hashes that those passwords are going to produce, right? If you had a unique salt for every user, you've multiplied the number of potential hashes by 10,000. And that just makes brute forcing or pre-computing any password guesses so much slower. Right? And when you combine that with a slow hash function that makes it hard to guess, no one's going to break into your passwords unless they're extremely weak.
So, I mean, I think the concern is if the attacker gets that file and can see what the salt is, can't they just reverse it? Or are you saying they can, it's much more work?
They can hash password guesses with the salt, right? So let's suppose my salt is 1234, right? They could try 1234 password 1, 1234 QWERTY, 1234 bad password, 1234 correct horse battery staple, right? And they can try with different ones. The salt doesn't add secrecy, it adds randomness. But for every single word that they guess, they have to put 1234 on it and try that hash. And then if you have a different salt, so maybe your account has a 1235 salt, they've also got to do that, which is double the number of hashes they have to compute. It makes the whole thing much, much slower. It offers no real benefit when you're guessing the passwords of one individual because you just add the salt to every single attempt. But if you've got more than one individual, it slows down your attack by that amount, right? Because of all the different salt and password combinations you're going to have to try.
So in other words, you can't use a rainbow table. You're forced to use brute force, which is slow and process intensive, etc.
If you only had a few potential salts, you could create rainbow tables for each of those salts.
Yeah.
But typically we don't do that. We have random salts, or we have many salts, or their username derives a salt or something like this to make sure everyone is different. And then there's no real way of pre-computing rainbow tables that way. So
just to reiterate, a hash function is non-reversible. You can't get the original data if you've got the hash because something is lost along the way. Yep. I love the example that you did with like a basic maths thing, right? What plus what equals 100? It depends, yep. Right? So I love that. Mike, I got to ask you this: what is Pigeon's got to do with hash functions? We talked about the birthday paradox, and that is the idea that the likelihood of collisions between hash functions is like surprisingly likely, considering that it seems so counterintuitive that you would get a collision. The pigeonhole principle, or the drawer principle, is just this idea that if you have a load of pigeons and you're trying to stick them in drawers or stick them in holes, you are eventually going to run out of holes, and then you have to have 2 pigeons in the same hole. Yep. So let's use a simple example. Imagine you've got 24 boxes, right? That you crate that you're carrying pigeons around in, right? You're doing your own racing pigeons. Now, I don't really know how racing pigeons work, but you tend to release them all. So you bring them all out in boxes, take them somewhere, release them. Now, you own 25 pigeons and you have 24 boxes. So the first pigeon goes in the first box, or a box of random, and you've now got 23 boxes spare. And the next pigeon goes in the next box, and the next pigeon goes in the next box. Now, after you've put in 24 pigeons, you are either going to have multiple pigeons in a box and some empty boxes, or you're going to have exactly a pigeon in every box and no spare boxes at all.
because you have 24 boxes. So where are you putting that last box, that last pigeon? Right? It has to double up. And so this is a way that people use to explain the fact that when you have more items that you're summarizing in a small space, you have to double up. And it's for hash functions, it's relevant because it guarantees you'll get collisions. This is what's kind of weird about hash functions, is we talk about these collisions, but the output space of a hash function is so big, you can't, it's unimaginably vast, and you can't think, how could we possibly get a collision, right? I mean, the output of SHA-256 is a 256-bit hash function. That's at least as many atoms as there are in the universe, right? So you think, well, it's all very well with me saying that technically things could collide, but how are they going to? The problem is you have a lot of potential messages, right? For a 5 gigabyte file, that is a lot more combinations of noughts and ones than there are fit into 256 bits worth of space. So if you give me enough Kali Linux distributions, I will find you a collision. Unfortunately, we could be here for quite a long time because the chances of that happening are really, really small, to the point where there's no point in trying. Unless we find some weakness in SHA-256 or our computers get so fast, beyond all imagining that we can brute force through this kind of amount, it's not going to happen. We know we're not even, even in the most optimistic case, we're nowhere near. Right? I mean, we're not anywhere near 128-bit. So the idea is there are going to be collisions because you have more possible messages than you have hash functions. But I wouldn't worry about it because the chances of you finding one is almost impossibly low. Right? You could win the lottery many, many times over, I'm afraid, before you'll find a hash collision.
So in theory, we have these problems with the birthday paradox and the pigeonhole principle, etc.
Yeah.
But in reality, if you use SHA-2, it's unlikely it's ever going to happen. Is that kind of fair to say? Yeah.
Yes, that's exactly it. So SHA-2's output is so big that essentially the probability is so low that you don't need to worry about it. It's a bit like saying if I had a 2 to the power of 256 sided dice, what if I accidentally roll a 1? Well, yeah, I mean, I guess that would be bad if you don't want a 1, but you've got so many sides on the dice, it isn't going to happen, right? It's not going to happen in your lifetime. It's not going to happen in the lifetime of pretty much the entire of humanity. So it's probably not worth worrying about too much.
You mentioned that SHA-3 is different to SHA-2. Can you explain why, or is there something interesting there?
So one of the interesting things about SHA-1 was there were some mathematical weaknesses found in the way that SHA-1 attempts to jumble up the messages it comes in, such that you could track some of those changes just a little bit, and that led to a collision. Right? Very hard to find a collision in SHA-1, but it's easier than just guessing until you get one. And I mean, the original Google attack is at the website shattered.io. You can go there and you can find 2 PDF files that look similar but not the same, and they have the same SHA-1 hash, right? And that shouldn't be possible because 160 bits is a very big output space. So that means that some weakness has been found in the algorithm, which means that they were able to find, with a lot of compute, but they were able to find a collision when they shouldn't have done. There's another weakness with SHA-1 and SHA-2, which is that they're vulnerable to something called a length extension attack, which is where if you give me a hash of a file, I might be able to obtain a valid hash of that file with a little bit extra on the end. And that could be a problem for example, our bank analogy that we were talking about earlier. You send me a bank transaction of £10 and I add a 0 to the end of it, right? We don't want to be doing that. So you usually design your system such that weakness of SHA-2 is removed, but nevertheless, it is a weakness, right? And so NIST, the National Institute of Standards and Technology, said, well, look, why don't we try and design a hash function as an alternative to SHA-2 if someone comes out with shattered2.io or comes up with some nice attack, in the future, right? We don't know if it will happen, but it could. Right? It's the same argument for post-quantum cryptography. Right? There is no.
Yeah, that's my next question. Yeah, what about quantum?
Right? Sorry, there's no quantum computer that breaks RSA today, right? But can we say there definitely won't be one in 30 years? No. Yeah. So we might as well look to future-proof just in case. Right? Now it might be we get in 30 years' time and there is no such quantum computer, and we didn't need to worry about it. But it doesn't hurt to be safe, does it? And so that's the same with hash functions. SHA-3 was specifically designed as part of a competition to be very different in structure to SHA-2. It's not vulnerable to length extension attacks, but it has all the same outputs. So there's a 256-bit version, a 384-bit version, a 512-bit version. And the idea is that suppose a website appears tomorrow with 2 PDFs that hash to the same thing in SHA-2, and we all declare SHA-2 as dead, right? And it's all a disaster. We can just go into our code and change all the 2s to 3s and replace the algorithm as quickly as possible, right? If we hadn't have done that, then we're always at this. There's always got this sort of small thing in the back of your mind of what happens if someone breaks SHA-2 tomorrow, right? What's our backup plan? It's always good to have a backup plan, particularly in cybersecurity, right?
Exactly, yeah.
Someone breaks SHA-2 out of absolutely nowhere. We didn't see it coming. We have that backup plan. As it happens, SHA-2 has been massively well tested over many, many years, and it's still holding up, right? So at the moment, there's very little reason to change all your code, but the option is there. Right? The option is there. If something happens or you decide you want to go somewhere else with it, you can use SHA-3 safely. Right? It's not been as well tested, but as far as I can tell, at the moment, it's safe.
What about quantum? Because you mentioned that, and I think the concern is, post-quantum safe is this term that people are talking about. So are these like SHA-1, I mean, MD5 is a waste of time, but like SHA-1, 2, 3, whatever, are they susceptible to quantum, or is it still theoretical, or are they like new algorithms to replace these in the future?
So one thing that's really interesting about quantum is one thing I think I see a lot of people, the mistake they make with quantum is they think a quantum computer is a really fast normal computer, right? They think that anything that's slow now will be fast when we have quantum. That's not actually the case. They're very, very different structurally. They have different kinds of programs, and there are some programs that don't exist on a quantum computer, just like there are programs that do exist that don't exist on a regular computer. So there are specific algorithms on a quantum computer that have been kind of designed, like Shor's algorithm and Grover's algorithm, that make certain parts of cryptography very, very weak if such a quantum computer is developed. But they have comparatively limited effect on other areas of cryptography. So, for example, AES, 128-bit AES becomes essentially a 64-bit problem if you have Grover's algorithm. That is breakable, right? But 256-bit AES becomes 128-bit, and that isn't breakable. So in some sense, AES is absolutely fine. You just use a 256-bit version. Hash functions, similarly, right? You just use the longer version. We all switch to SHA-512. It's like no big deal, right? Public key, that's a much bigger issue, right? So public key cryptography, Diffie-Hellman key exchange, RSA, elliptic curve cryptography, these are all made fundamentally weak if such a quantum computer exists, which is why so much effort is going into developing new versions of these algorithms that are resistant. And actually, using hash functions as a core of that process is one of the ways people are looking at making these things quantum resistant, right? Hash-based signature schemes aren't susceptible really to quantum computers.
That's good to know. So I think we should cover PKI in a separate video, and
sure.
like quantum and the issues with that. So just to summarize, and for everyone who's watching, put comments below so I can ask Mike more questions. You've covered the fact that a hash function is a one-way function. So for everyone who said that, that wasn't true, here's the answer. Rainbow tables aren't cracking hashes or going in the reverse. We've covered that. So hash function is always fixed length, right?
Yeah, it's very useful. Right, there's other reasons to use hash functions beyond simply the randomness they provide. The fact they're fixed length is very helpful for things like digital signatures. If you've got a very long document and you want to digitally sign it, it's not easy to algorithmically sign an extremely long document. Let's say the Kali installation of 5 gig. What you do is you summarize it in a very short hash function and then you sign that. Right? And so it's very helpful for those hash functions always to have the same length because your algorithm is always very predictable, right? And it fits neatly into like messages and things like this.
So explain signing, because just for people who don't know what that is, how does a digital signature actually work? I'm assuming you're signing with something, right? Yeah,
you're signing with the private key. So it's a branch of asymmetric cryptography. That means you have, instead of just one encryption key that encrypts and then decrypts again, you have two. You have a public key that I send to you, and you have a private key that I keep to myself. And then what I do is I digitally sign a document or something that I need to prove using my private key, and then you can use my public key to verify it, right? And then then you get into PKI, so like certificates and things that are to do with how we distribute public keys. It would be too simplistic to say that digital signatures are the same as encryption, kind of in reverse, right? Yeah. It's more complicated than that. But hash functions are a really important part of that process because you usually summarize the document first, maybe you add padding, you do other things, but the hash function is part of that process before you actually compute the signature with the private key. And so the fact they're a fixed length is super useful. The fact that the chances are two different files are going to have different hashes is also very, very useful, right? Finding a collision would cause a real problem for digital signatures because the signatures would be the same, right? My private key is the same. These two documents hash the same thing. So the signatures are the same. And that means you would verify both of them using my public key. And one of them might be nefarious, right? So that's where it would cause a problem.
Mike, you mentioned this right in the beginning. You spoke about this avalanche effect when you changed the works of Shakespeare. Can you explain what is the avalanche effect?
Yeah, and actually the avalanche effect is really important for encryption algorithms as well, right? The idea that a small change in the input leads to a big change in the output, right? So your output of your SHA-256 hash function is 256 zeros and ones, right? So imagine those 256 bits written out on a piece of paper and they're just sitting there. You change one bit somewhere in the entire works of Shakespeare and the hash completely changes. Half of those noughts and ones are flipping randomly, right? As if someone's just coin flipping and just producing it at random. And the only way you can achieve that, because actually the input change is not very big, right? The input change is one bit in this giant file. It's because that bit has a huge effect on what the eventual output will be, because it gets mixed in, it gets moved around, it gets combined with other bits. And that happens to all the bits throughout the whole message. So part of the interesting design of a hash function is how do you get the bits to propagate around the output as fast as possible, right? And that's called the avalanche effect. It's also important in encryption, right? So imagine you have a AES, right? It's got 128-bit block size. So you're encrypting, let's say, 128 bits of your really obvious message, and you want 128 bits of nonsense. You want to, if you change one bit of the secret key or one bit of the message, you want a completely different output. Because otherwise, you could imagine you'd be able to map it backwards. You go, well, actually, only that one bit changed, and I know that means the key is this, right? It's because they look so random and so much changes so unpredictably that you cannot reverse those processes, right? So that's the strength of hash functions. Because the output is so unpredictable, it means you can't reverse it, because you just cannot follow that kind of weird mathematical or computational equation that's just so complex you can't imagine it, to go back from these random bits all the way back to a nice predictable input.
And this is just maths, right? Or math from our American friends. It's just
maths and permutation. So, I mean, I give you an example. So the SHA-256 hash function uses various operations inside, but the ones it uses a lot of are bit rotation. So you take some bits, you move them, and then you wrap them back around again. Adding things together. So taking two bits and taking two integers or two sets of bits and bytes, adding them and discarding any carry bits, right? By discarding the carry bits, you're throwing away information, which makes it much harder to reverse. And the other thing they do a lot of is XOR, exclusive OR. So taking two sets of bytes and bits, XORing them together. And again, that is a reversible process, but built into these others, it becomes unmanageable. And so actually, because they're designed to be quick, right? We don't want to, most people, I think, could design a reasonable hash function if they had, if it didn't matter how slow it was, right? If it didn't matter how slow it was, you could just keep jumbling things up until it was nonsense. The problem is that it has to also be quite quick, because when we use SHA-256 to perform digital signatures, or we use it to verify passwords, usually people don't want to have to wait too long to have those things come back, right? In actual fact, you often hash multiple times to verify passwords because it's more secure, but not too many times, right? We don't want to slow it down. So, part of a hash function is a compromise between this avalanche effect, propagating from the input to the output as quickly as possible, but while also doing it as fast as possible, so that it's really, really efficient.
So if I want to learn how hashes work, can I attend one of your classes, or how do I learn this stuff? So
I've done quite a lot of videos. I've done quite a number of videos on Computerphile about hash functions. I teach hash functions in my own course because they're a huge fundamental part of cryptography. I've actually implemented most of the hash functions. I'm a bit weird. I find these things fun, but I also find that by implementing things, you understand them really, really well.
Exactly. Yeah.
actually, conceptually, SHA-256 and SHA-512 are not that complicated, right? They are simple structures designed in a very clever way. If you go and look at the Wikipedia page for SHA-256, the source code is there, right? The pseudocode is there. You could implement it in your preferred language and you will find it works, right? And it's quite satisfying when you hash the entire works of Shakespeare and then out comes a hash that you know is correct, right? And it's a really good way to understand how these things work. Just try now implementing the opposite. Try going from that hash and thinking about what program you would write to go backwards to the entire works of Shakespeare, and you realize it can't be done. There's no information left. You've got 256 bits of random noughts and ones. How do you get back to all these, incredible books? Not easily.
Dr. Mike Pound, I want to thank you for sharing. What I really appreciate is, number one, you're very humble. Number two, you can take this complex stuff and make it simple so that all of us can understand. Thanks so much for sharing.
No problem at all. See you next time.